Okay, we are back again. So, for this one, that swing equation during fault, same thing we will write, only thing is that this is your PM2, it is nothing but your PG2, right, and this is your PM3, it is nothing but your PG3, this data were given earlier, right. So, and when you make this one, and this is your H1 and H2, sorry, H2 and H3, that is inertia constant. Now, for after that your this is swing equation post fault condition. So, during fault also we have got this swing equation. So, during fault we have got this swing equation. So, we have to see that fault clearing time. So, how long this fault is persisting, right, and when fault is cleared, then automatically it will move to this equation. So, code and other things cannot be done in this course, because it will be then something different. So, only I have to look into that from the point of view of classroom exercise, but this example I took just that such that your how to call that all ideas, our ideas will be clear, right, only up to this. So, with that transient stability chapter will be closed, but I suggest that before moving to the next chapter, I suggest that whatever has been given, just you pick up any book that multi-machine system and transient stability, you can get any book and just have a few small problem, 3 bars 4 bars problem, and try to derive those swing equations and how these things are, all these things are coming, right. With this we will close the transient stability chapter, and now we will move to the your automatic generation control or load frequency control, right. So, next is your automatic generation control. So, we have actually just before going to all this, that whenever we are studying, it is automatic generation control in deregulated environment. So, at that time your what you call that we have to first start with your conventional scenarios. So, whatever little bit here you will see, it is your what you call write up and everything. So, first we will go to that conventional AGC, because up from there we will move to your deregulated environment. Two different version we will see regarding your this AGC in your restructured or deregulated environment. Only we will restrict our analysis to the steady state part only. Simulation part cannot be done in this video course, it is not possible actually, but I will show you some simulations. And generally that we sometimes we call it as automatic generation control, and sometimes we call it as load frequency control. So, basically when we call automatic generation control, that basically is, I mean in my words, it will be load frequency control plus economic load dispatch together will be automatic generation control, right. But when economic load dispatch will not be done here, so we will consider that automatic generation control and load frequency control both are same, right, and in that means we will term this as automatic generation control, right. And because in power system actually continuously that loads are changing, right. I mean continuously loads are changing, because many loads are getting switched on or switched off continuously, and that is why a continuous disturbance will be there, right. But when this disturbance is very small, I mean in terms of say small compared to a large load, if there is a small change in load, then basically what happens, that small change in real power basically it affects the your system frequency, but leaves the bus voltage magnitude almost unaffected. Similarly, if there is a small change in reactive power, then it affects the bus voltage magnitude, but leaves the system frequency unaffected, hence that your voltage angles, right, are almost unaffected. So, that is why that your real power frequency control and reactive power voltage control, these two things are treated your separately, that is they are decoupled, right. So, in this case your what you call first is introduction part, right. So, an electric energy system, just I am underlying few things. So, an electric energy system must be maintained at desired operating level characterized by nominal frequency, voltage profile and load flow configuration, right. It is kept in this nominal state by close control of the real and reactive powers generated in the controllable sources of the system, right. The generation changes must be made to match the load variation at the nominal condition, right. So, if the nominal state is to be maintained, that means if there is a, suppose if there is a increase in the load, right. So, that means immediately there will be a transient imbalance between generation and load, because load will be more, generation will be less, right. So, transient imbalance will be there. So, therefore, generation will chase the load. Sometimes we call this is load following, when generator is following the load. So, deregulated environment we will also see the load following, right. The control of an electric energy system in order to achieve an exact matching of the generation to load at nominal state is a very complex problem, right. So, just hold on, we will move it up. Right. So, the generation, so what happened that your, so the load changes actually we will go to this, the load changes actually I told you the continuously, right. So, if you and they may be considered as essentially constant with superimposed first order perturbation delta P d and delta Q d respectively, right. So, for a small mismatch, your small perturbation, a mismatch in real power balance affects primarily system frequency I told you, but leaves the bus voltage magnitude essentially unaffected, and similarly a mismatch in reactive power balance affects mainly the bus voltage magnitude, but leaves the system frequency essentially unaffected, right. So, in that case, so in view of this, the real power frequency control and reactive power voltage control, right, problems are treated as two independent as decoupled control problems for all practical purposes. So, the change in turbine power output, that is actually that is your mechanical power output, right, results due to governor and speed changer actions. The generator response is for all practical purposes instantaneous, and hence changes in turbine power output causes instantaneous change in electrical power output. We are actually considering it is a lossless turbine, right. So, we will move next. In any power system, it is desirable feature actually to achieve better frequency constancy than is obtained by the speed governing system alone. So, in an interconnected power system, it is also desirable to maintain the tie line power flow at schedule level irrespective of load changes in an area. That means, two power systems are there, later we will see, and they are interconnected by three phase line, we call tie line, right. So, I mean you have so many power systems are interconnected together, and whenever one particular power system we call an area, right, when it needs power from the other area or it buys power from the other power system, right, that has to be maintained, that scheduled power has to be maintained, right. So, irrespective of load changes in an area. To accomplish this, it becomes necessary to automatically manipulate the operation of main steam valves in case of a steam power plant, or hydro gates in case of a hydro power plant, in accordance with a suitable control strategy, which in turn control the real power output of electric generators, right. The problem of controlling the real power output of electric generators in this way is termed as automatic generation control, right. So, in this case, the problem of controlling the real power output of electric generators in this way is termed as your automatic generation control. This is some kind of definition. Now, whenever we will study this one, that throughout this deregulated environment, that we will consider only your steam turbine, right. If time permits, then hydro turbine modeling at the end of this course I will do it for you, and hydro turbine modeling, some special feature is there for hydro turbine modeling. So, as it is a your stability and this thing, so if time permits only at the end I will see first after all this deregulated environment, and also little bit half an hour or so I will see that reactive power voltage control also little bit we will see, and after that state estimation, and after that if time permits excitation system and this hydro turbine modeling and AGC how things are, that will be at the end if time permits, right. So, now basic your what you call next is basic generator control loops, right. So, in an interconnected power system, load frequency control and automatic voltage regulator equipment are installed for each generator. This though we have seen AVR and another thing for that initial lectures, right, first 14 lectures, more than 14 lectures, right, all AVR other things we have seen, right, and installed for each generator. That figure 1 I will come to that, gives the schematic diagram of the LFC loop and AVR loop. The controllers take care of small changes in load demand to maintain the frequency deviation and tie power deviation within the specified limits, right. So, before going to that, this is the your what you call the schematic diagram, right. So, just let me reduce its size, right. So, if you look at the schematic diagram, we will come to that right up later. If you look at the schematic diagram, this is actually just showing for steam power plant steam, right, and one LFC controller is here, load frequency controller is there, and this is actually what happened, that it is sensing the frequency from here, frequency sensor is there, and delta F and delta p tie, this combination is taken. How it is taken we will see at the end, and output is actually delta P c. This is actually whatever signal is getting, this is valve control mechanism, right, and this is steam is according to these signals that opening or closing, it will dictate the opening or closing of the steam valve, right. Then it is coming to the turbine, then shaft is there, then the turbine and generator coupled together, right, and in power plant there is no gear mechanism for this, right. So, the turbine and generator, and then the 3 phase terminals are there. So, this is delta P g plus J delta Q g, right, and from here that voltage sensor is there, that this is delta V, then automatic voltage regulator is there, and then delta Q C I, this is excitation system for the generating system generator. So, this is basically generator field, this is a schematic diagram, right, and we will not consider that this part, we will not consider that this part, right, because we will treat it as a separate thing. Actually why we decouple it, that particularly the excitation side, the time constant of all these things are very small, right. So, whenever AGC action start, before that their dynamics will be over, their transient part will be over. So, almost they have no effect on AGC. So, it is basically decoupled, right. So, so this is the schematic diagram, but here that your here that for small changes in real power, whatever I said, the small changes in real power are mainly dependent on changes in rotor angle delta, hence the frequency, right. The reactive power is mainly dependent on the voltage magnitude, that is on the generator excitation. The excitation system time constant is much smaller than the prime mover time constant, and its transient decay much faster and does not affect the LFC dynamics, right, that is I told you. So, thus the coupling between the LFC loop and the AVR loop is negligible, and the load frequency and excitation voltage control are analyzed independently, right. So, when I was very young at that time, I developed this model that your what you call considering that reactive power demand, the coupling thing, and I simulated it. I found that your due to real power changes, the voltage deviation is very negligible. Similarly, for small reactive power change, the deviation in frequency is almost negligible, right. So, that is why these two are treated as decoupled, right. That means several years back when I was very young, at that time I tried to develop this, right. So, this is that I explained this one, right. So, next is your what you call, after this we will come to another term called isochronous governor. Isochronous means the constant speed, right. So, meaning of this isochronous means that constant speed, right. So, an isochronous governor adjusts the turbine valve if it is a steam turbine, or gate means if it is a hydro turbine, hydro gate. That is why valve means when I write valve means it is steam valve, when I write gate means it is hydrogate for hydro turbine, right. So, to bring the frequency back to the nominal or its scheduled value, that is right. The figure 3 will come later, shows the schematic diagram of isochronous speed governing system. I will come to that, right. The measured frequency f or speed omega, whichever you take, either you take f or you take omega 2 pi f, right, is compared with reference frequency f r, that is a reference speed or omega r, f r or omega r, that sub reference speed, it will, with that it will be compared, right. The error signal whatever is comes equal to frequency deviation, or sometimes we call speed deviation. If it is a frequency deviation, suppose f is the frequency and f r is the reference frequency, say f minus f r, and if it is a speed you take, then omega minus omega r, right, is amplified and integrated to produce a control signal delta E, right, which actuates the main steam supply valve in the case of a steam turbine or gates in the case of hydro turbine, right. So, we will go to that figure 3, right. So, this is actually figure 3. So, this is your, this is valve if it is a steam turbine, and this is gate if it is a hydro turbine, hydro gate. And hydro modeling, hydro turbine modeling is very interesting. It is called non-minimum phase turbine model. What is the meaning of that? Those who are studying control system, they will be knowing the meaning of non-minimum phase. And hydro turbine has a period initially for any load disturbance has a different characteristic. If time permits, at the end I will do it for you, right. So, this is steam or water, and this is your turbine, right, and it is Pm, that your power output, and this is generator, and this is P. We are neglecting the any loss in the turbine, right. So, P is equal to say Pm, and then this frequency is sensed because it is turbine generator is a rotating shaft, right, rotating shaft, and your frequency is sensed from that one. So, this is the frequency is measured, say f, right, and this is a reference frequency, that is you have set, that is your set point, and you are comparing these two. So, f minus f r, and it is amplified, say gain is given, suppose some minus k gain is given, and this output here is delta f, and one integrator is there, and output of this one is delta E, the valve or gate position, right. And according to this signal, this opening or closing valve for steam turbine or for hydro gate, it will depend on according to the signal, because if load increases, real power load increases, the frequency falls. This is a question to you, that if load increases, that frequency, hence the speed actually decrease for the your alternator, but question is that it will never lose synchronism, but it will decrease, right. And if load your decreases, then opposite happens, right. So, frequency increases, hence the speed increases, right. So, why it happens, that what is the philosophy behind that is a question to you, right. So, according to the whatever output signal it will get, according to the valve or gate opening and closing will be decided by this signal, and then this is turbine, and this is your what you call schematic diagram of a isochronous governor. So, in this case, for the case of isochronous governor, it is called constant speed governor. So, and isochronous governor works very well with a generator is supplying an isolated load, right, or when only one generator in a multi-generator system is required to respond to changes in load, right. You can use this one, but it is only supplying one load, or in a your what you call in a group of generators, right. When is required to, out of so many generators are there, but when only one generator in a multi-generator system is required to respond to changes in the load. However, for load sharing between generators connected to the system, right, droop characteristic or speed regulation must be provided as discussed in the your next section, right. So, a droop characteristic will be there, otherwise what happen, there will be a tug of war between the generator, between that your what you call generator. Suppose load has increased, so every generator has to share power among themselves, right. So, and every generator you are setting some reference set point, right, and that is manually you are doing it. And if manually when you will set the reference set point, there is every possibility that all the generators, it may not be exact, right, it may not be exact one. So, there will be tug of war then, because every generator will try to pull it to its own side. So, that is why we need a droop characteristic for the governor. So, governor with speed we call speed droop characteristic, or sometimes we call speed regulation parameter, or sometimes we call your what we call simply regulation parameter. So, when two or more generating units are connected, when two or more generating units are connected to the same system, right, isochronous governors cannot be used, since each generating unit would have to have precisely the same speed setting, right. Otherwise, they would fight each other. Each will try to control system frequency to its own setting. For stable load division between two or more generating units operating in parallel, the governors are provided with a characteristic so that speed drops as the load is increased, right. So, some additional feedback is required, right, then only things will be balanced. So, the regulation or speed loop characteristic can be obtained by adding a steady state feedback loop around the integrator as shown in figure 4. I mean, here earlier for isochronous governor everything was there, this part was there, everything was there, right. But to make this your what you call, you have to add a steady state feedback loop around the integrator. That means, this this feedback is taken, and this R is called sometimes speed loop parameter or regulation parameter, right, and this feedback is given here. So, that means that whole governor portion actually is this much, right. So, what we will do in the next diagram, this portion will bring it to the left hand side. I mean, it will just make this just opposite way, I mean 180 degree shift, right. So, this one, this is your delta f, this is integrator gain, right, and this is minus, and this is integrator. So, we will make just in this one will bring to the left hand side, and this one will take to the right hand side in the next diagram. So, this what I told you, that this one is delta f, this is delta f, right, and your this is k integrator, right, that is 1 upon s. So, this is your delta f, and if you look at the feedback, delta f has a minus sign here, and R is also minus sign here, right, and so delta f both minus sign is here, then k that gain, right, and integrator 1 upon s, this is delta E. From here this output R, this thing R feedback is here, right. So, this is your simply the block diagram of the governor, right, and your if you simplify this one, if you simplify this block diagram, then what will happen, that if you simplify this one, that your it will come like this, delta f, then 1 upon 1 minus 1 upon R, 1 upon 1 plus S T G delta E, where your T G is equal to 1 upon K R, the governor time constant. Actually, this one you simply this one you simply yourself you can do it, right. So, just you the way you have done that your control system, that block diagram output by input, same way you can make this one also. I have not done it here, a small thing, that is why I have not done it here. Simply I have written that your delta f, this will become actually minus delta f by R. So, delta f is the input. So, minus 1 upon R into 1 upon 1 plus S T G, and T G is nothing but 1 upon K into R, that is governor time constant, right. So, and R is the speed regulation parameter. Now, next is the speed regulation, that is the droop, sometimes we call droop parameter, right. So, the value of speed regulation parameter R actually it determines the steady state frequency versus load characteristic of the generating unit as shown in figure 6. I will come to that figure 6, right. The ratio of frequency variation deviation, that is delta f, to change in valve or gate position delta E or position or power output delta P G is equal to R. The parameter R is referred to as the speed regulation or droop parameter, or sometimes we call speed regulation parameter. It can be expressed as the percent R, this percent R, right, is equal to the percent frequency change by percent power output into 100 percentage, right. So, this is equation 1. So, that means your meaning of this one I will come later. So, for example, if you go to this figure, that this is actually frequency, this side is my frequency and this is my power output, right. Power output, or just hold on, let me move it little bit up, right. So, this is my frequency and this is my power output or valve or gate position, your PU. In per unit you will find that they will be same, right. So, and this is FNL means, NL means that is your no load frequency, right, and FL means the full load frequency. So, you and the droop characteristic is almost this is your linear. So, and this is your maximum power output in per unit 1.0. So, and this is my nominal frequency, that is F0, and this is your FNL, this is your FNL and this is a full load, right. So, at no load means, so when power is 0, frequency is like this, right, and when it is nominal operating at nominal frequency, this power is this much, right, and when it is full load, so this much frequency drop from here to here, right. So, in this case delta f is equal to, for some frequency f, it is f minus f0, because f0 is the nominal system frequency. Say if it is a 50 hertz, it will be 50 hertz, if it is a 60 hertz system, it will be 60 hertz, and then r, the slope r will be delta f upon delta p. So, this difference is delta p. So, this is delta f, right. So, basically this is also delta f. So, r is equal to delta f upon delta p, right. So, f0 is equal to, sometimes we call scheduled system frequency or nominal system frequency, right. So, this is actually figure 6, this is a steady state characteristic. So, for example, that is the meaning of equation 1, that a 4% droop or regulation means that 4% frequency deviation actually causes 100% change in valve position or your power output. For example, suppose if this is your what you call, that is your 4% change, this is your 4% change in frequency, that is nothing but 2 hertz for your 50 hertz system, and if it is a 60 hertz system, then it will be 2.4 hertz, right, because 4% that is 0.04 into 50. So, 2 hertz. For that, if it happens that there is a 100% change in power output, that is your 1%, that is 1 per unit is given, that 100%, right. That is the meaning of that equation 1. So, thank you very much, we will be back again.